This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Good evening, my name is Nigella Hilgarth and I'm the Executive Director here at the Birch Aquarium. Delighted to see you all here this evening for the latest Perspectives on Ocean Science Jeffrey B. Graham Lecture Series. And it's my great pleasure this evening to introduce our speaker, Dr. Neal Driscoll. Neal is a professor here at Scripps Institution of Oceanography. He's a professor in the geosciences. And he got his bachelor's degree at the University of New Hampshire and his master's in Rhode Island, and then he did his PhD at Columbia University. And I gather he was at that little place called Woods Hole for a while, but we don't talk about that too much. And I'm very excited because this evening he's going to really tell us some very new cutting-edge research that I believe hasn't even been published yet. And so without any further ado, please join me in welcoming Neal in unraveling the secrets of the southern San Andreas Fault.
Thank you, Nigella. It's always a pleasure to come here and talk. So many supporters, and it's fun for us scientists to get out and talk with you people that are so staunch in your support for Scripps, so I thank you for that. So today, I'm going to talk to you about some new research. We just submitted this to Nature Geoscience. We're going to propose to you that the Salton Sea is the pacemaker for earthquakes on the southern San Andreas Fault. And science is conducted by groups. So before I move forward, I'd like to acknowledge my co-authors and colleagues, Graham Kent, Danny Brothers, Debbie Kilb, and Karen Luttrell, and I'll try to outline during the course of this talk where their contributions have pushed this science forward. This is a picture of the sprawl. This was back last year. Student of mine, Jillian Maloney, here's me in shorts. Alan Jaffe, right here, sailed with us a number of times. Alan's a great guy, a big supporter of Scripps, and a good friend, and I miss him. So I'd like to dedicate tonight to Alan. Okay. So the Salton Sea, largest body of water in California, 35 miles long, about 15 miles wide in its southern part, and it's all about the water. It's all about balancing the water, balancing it for irrigation, balancing it for preserving habitats, balancing it for metropolitan regions. I'm going to tell you tonight, the water also can trigger earthquakes. Okay, so if you want to get home early and look at Kathy Constable's talk, I'm going to give you the punchline now, and then I'm going to tell you how we got to this result. So we believe that the Salton Sea may act as a catalyst in triggering earthquakes on the southern San Andreas Fault. So as the Colorado River switches its course from the Gulf of California north into the Salton Sea, it fills it up. Fills it up about 100 meters with water and puts this weight on the plate. We believe this increased stress on the plate may help trigger earthquakes on the southern San Andreas Fault. We believe the diversion of water away from the Salton Sea for about the last 100 years is the reason that this fault is about 100 years beyond its recurrence interval. So diverting the water has actually changed the time between earthquakes. This is somewhat good, but somewhat bad, because Our predictions say that the longer we wait for this next earthquake, the larger it will be. Okay, so we've changed the rate at which the earthquakes happen, but we might have also changed their magnitude. That's our story tonight. Okay, so in plate tectonics, we're going to just backpedal a little bit so that we're all on the same page. Earthquakes, shown in this picture here, larger than magnitude 5, delineate the plate boundaries. So here, just showing the boundary between the Pacific and North American plate, it's outlined by these earthquakes. Okay? There's 3 major types of plate boundaries. There's plate boundaries where the plate is subducted and recycled back into the earth. These are the subduction zones. These are the source of the great earthquakes. Okay? There's also parts of the plates where they're pulling apart, mid-ocean ridges. Okay? These earthquakes are much smaller. They're in the order of magnitude 5 or 6. And then we come to California, where the plates slide by one another. Strike-slip faults. These have characteristic magnitudes of 6 and 7s. Okay? All right? So earthquakes delineate the plate boundaries. The Pacific plate is moving to the northwest with respect to the North American plate. It's moving at about 50 millimeters per year, about the rate your fingernails grow. Okay? All right, now here is a couple of animations just to show you some of the history of our plate boundary. The plate boundary used to be a subduction plate boundary, the source of great earthquakes, and it's changed through time because the buoyant hot ridge didn't want to be subducted. Imagine trying to hold a big piece of styrofoam down on the bottom of your pool. It takes a lot of work, okay? That's kind of the amount of work that it would take to take a buoyant hot ridge and recycle it back into the earth. So here, Tanya Atwater's movie here shows how this plate boundary evolved through time. Time here is on the y-axis. We're going to start at about 38 million years ago. So here we go. So I'm going to do 38 million years in about a minute. So here we're subducting the plate. It breaks into the Juan de Fuca plate. We start building the San Andreas Fault. You'll see Baja peel off here. Okay? You'll actually see the transverse range rotate around. This light pink area is where we're having extension in the Basin and Range Colorado Plateau. So here to the north in Northern California, we still have subduction. Okay? And here is a long strike-slip fault that connects up into the Gulf of California, which is segmented ridges. Now this other movie is by Warnke and his group and just delineates this in a little more detail. The time scale falls from the top to the bottom. This shows some of the rotation. So pay attention to the red because these areas actually rotate 90 degrees as the plates move by one another. So this is Santa Barbara Basin, Santa Ynez Mountains. You can see here Baja, okay, Sierra Block. Okay, so we've had a lot of activity here in California over the last 30 million years. So how many people felt the 7.2 Sierra El Mayor fault on Easter? Okay. How many thought it was the big one? I did. I left an Easter party and went home and said, darn, we didn't get the experiment in before it ripped on the southern San Andreas. Okay? So I had mixed feelings. So here, when you have earthquakes like this, the mountains shake, the loose gravel and rocks kick up dust clouds. If you go on YouTube, there's a video that has a lot of expletives in it. I didn't think I needed to share that with you. Okay? So here, the mountains actually have dust clouds during the earthquake. It's an amazing thing to watch if you're far away and you're not in a high rise. Okay? Cracks, some of my colleagues drive into these. Okay? A lot of road damage. But the thing I want to bring up to you is something called liquefaction. Okay? So liquefaction is when you have liquefied sand and you have the earthquake waves. This sand actually turns into a fluid. the ground loses strength. These things actually go up through fissures and dikes and actually have a little sand blow that looks very reminiscent of a volcano with a crater. This wreaks havoc on infrastructure, such as canals and waterways, okay? So this affected regions 60 miles away from the earthquake. So liquefaction is something that we should worry about. So where we have soils that are susceptible to this can cause weakening of structure, subsidence, deformation, okay? And this can happen far away from the epicenter. Okay, so what is the epicenter? The epicenter is where we project the earthquake which occurs at depth to the surface. So we have some geographical bearing on where it happened, okay? What have we learned from large earthquakes in California? A couple of things. Where they happen is critical to the loss of life and damage to infrastructure. Okay? All right, so you can have a large earthquake, the Fort Tejon earthquake, magnitude 7.9. It had 6 to 9 meters of lateral displacement. Okay? All right? But look, 2 people died. That's because it happened in 1857 here, and Fort Tejon was the nearest place, but there weren't many residents. Okay? Think about the Haitian earthquake. Smaller, huge loss of life. Okay? Building structures. It was right underneath a populated area. So where an earthquake happens is really important. We learned this from the 1906 Great San Francisco earthquake, about the same size. Huge loss of life and damage to property. Loss of ability to fight fires. This caused a lot of the deaths, okay? We look at another large earthquake, the Lone Pine earthquake, which is right here on the eastern Sierras. This is the scarp, okay? This scarp is 4 to 5 meters high, and there's approximately 10 to 15 meters of lateral motion, okay? This is a large earthquake, okay? All right? 27 dead, all right? Again, look at when it happened. So one thing I'd like you to take away from this talk is earthquakes, magnitude is important, but where they occur is just as important. Also, California has been a leader in developing earthquake-proof properties, or at least reinforcing buildings so they have a better chance of standing up through the earthquake. Loma Prieta earthquake, also known as the World Series earthquake. Who was playing in this World Series?
Oakland and the Giants.
Oakland and the Giants. So this fall, I was sitting there going, oh, not again. The Giants, here we go again, okay? All right, well, at least this time they won. So here, the epicenter's down here in Santa Cruz, and I'm gonna show you the damage up in the Marina District due to liquefaction, okay? So here we're gonna start this movie. We're gonna start the earthquake. So you can see here the shaking velocity. It's gonna start here. You're about 60 miles away from San Francisco. It started down by Santa Cruz. This here is showing the shaking intensity as it propagates northward. This here is the Marina District, okay? A lot of collapse. A lot of the death happened far away from the epicenter. So again, liquefaction, substrate's really important. That's another point I'd like you to take away from this talk. So here, a lot of the building, bridge collapse. Okay, now watch these guys. If your house looks like this, the last thing I advise you to do is run underneath it with 2x4s. Okay, all right? Not good, safe earthquake practice. Northridge earthquake. Most of the earthquakes I've been talking to you tonight about are what we call right lateral. So if you're standing on this block, the road or adjacent features are displaced to the right, and it's independent of which block you stand on. Well, the Northridge earthquake was a blind thrust earthquake, okay? A different style of earthquake, but just as deadly. Caused a lot of damage and property, highest measured G. Okay? So we also have these style of faults here in Southern California. Okay? So here's the tough part of this business. Where's the future catastrophe going to happen? We cannot predict earthquakes. Okay? So we can look at a number of earthquakes. We can look at the San Andreas, potentially a 7.8. The Hayward Fault that goes right under UC Stadium, right under the goalposts, gives rise to the Stanford Catastrophe play. Okay. You have here the Wasatch Fault, right here at the foothills, okay, Salt Lake City. You have West Tahoe work that we've been doing up here that shows that this could have a potential magnitude 7.3 and associated tsunamis. But we can't predict where this next catastrophe is going to happen, okay? So a few things so we're on the same page as I try to discuss what we do and how we try to ascribe probability of where the next large earthquake is going to happen. So first, stress and strain. So here, this block sits here, and because of its weight, it has a certain friction on the table. I have to pull this string with a certain stress until the stress exceeds this frictional force. So the stress builds up, okay? Then the block moves. That's my earthquake. That's where I have strain. So the block doesn't move at all till I have the earthquake, and then the block moves very rapidly and then stops because I have a stress drop. All of a sudden, the stress that I'm pulling is less than the frictional force, and the earthquake is over. Okay? I then build up stress again, and I exceed the frictional force, block moves. So stress is the force per unit area, strain is the deformation. A few other things that scale with earthquake size, okay, and the one I really want you to focus on is the longer a fault is, the larger the potential earthquake. So earthquake magnitude scales with the length of the fault and the magnitude of slip on that fault. Okay. Other things here play a role, but that's the one I'd like you to take away tonight. So my group, what we do is we look at the sediment layers. We read them like tree rings of the earth. We try to reconstruct when paleo earthquakes occurred. Okay? How long between these paleo earthquakes, and how far did the plate move? By knowing this, we get some estimate about when the next earthquake might happen. Is there a probability it's 100 years out? 500 years out? Okay? If you look at the Rose Canyon fault here moved about 8,000 years ago. Moved a few hundred years ago, and it moved, we believe, somewhere in between those two. Some people would say that that's a long recurrence interval, and therefore the next large magnitude 6 earthquake on the Rose Canyon Fault won't be for another few thousand years. Other scientists say that maybe earthquakes cluster, that they come in bunches and groups. So maybe the one that happened a few hundred years ago is telling us that maybe another one's going to happen. We cannot predict earthquakes. Okay? We try our best to understand these recurrence intervals, try to estimate the magnitude, try to understand the plate motion, and try to put this all together in probability functions to develop some awareness and preparedness for earthquakes. So what we do is we measure these layers in the sediment. We sediment core. We use LIDAR to look at how channels are offset. We date events on the San Andreas. So the last 5 major earthquakes on the southern San Andreas happened every 200 years. Okay? We haven't had one now for 320 years. I could make all sorts of analogies with women that are 13, never mind. Okay. All right, so here to study earthquakes, we go to places that have sedimentary records, because the sedimentary records are the tree rings of the earth. So we go to places like Baja. Tough job, huh? Beautiful stratigraphy. Okay. Where's this? Mono Lake. So we work there. Go skiing, survey in the afternoon. Okay. It's a tough life. Okay. Where's this? Lake Tahoe. Oh. Ski areas. Neal, survey. Okay. All right. So lakes have incredible, robust stratigraphy that we can read and understand previous tectonic deformation. Okay. All right. Let's see if you can guess this one. This is my favorite. Okay. So here we go. Let's see if, where's this? It's the title. Salton Sea, yeah, okay. All right. If you're far away from it and you can't smell it, it's a wonderful place. Okay, so here, SDSU, SCEC, the Southern California Earthquake Center, the USGS, they've been doing a number of predictions of ground shaking using supercomputers. And something new has evolved in this field of research that tells us not only where the earthquake occurs, the type of sediment or rock where it occurs, also which direction the earthquake propagates is important. Okay? These red faults here have almost 100% probability of rupturing in the next 30 years. So we're down in here. So here in this movie I'm going to show, this is from the SCEC, we're going to show rupturing from the Salton Sea up here on the dotted line, and we're going to look at the energy that propagates into LA. Okay, so here we're going to look at ground shaking times up here. We're going to look here both interior and surface deformation. And here we're rupturing. We're 30 seconds into the earthquake. We're still rupturing the ground. Okay, so now the rupture stops. This is kind of like the bow wake in front of a boat. So here we're still propagating riverside, highly populated areas. Los Angeles, look at the rippling. We're a minute and a half out. But look at us down in San Diego. Really good. All right? They're still rippling. Look at this, okay? We're almost 2 minutes out, okay? 2.5 minutes out. So LA, because all the energy is funneled in that direction, and the substrate, LA has a lot of fill, sand layers, okay, harmonics, okay? So LA and Riverside, if the earthquake propagates from south to north, it's going to experience a lot of ground shaking for a long time. This is for a magnitude 7.8. Now here, remember, San Diego, blue and black is good, okay? All right, so this is a simulation if it propagates from northwest to southeast. LA does a lot better, so does Riverside. We're good in both scenarios, okay? Modulation. So here, this one shows if it propagates from the southeast, look at LA and Riverside. Look at the difference in energy patterns. We're starting to realize that the propagation direction of earthquakes is also important. So our research tried to look and see if there was any hints in the sediment record that would tell us whether a south to north propagation could happen or vice versa. Okay? The Salton Sea is a really interesting place. Okay? There's no boats. There's no people out there. We're the only vessel on the ocean when we're out there on the sea. Okay? It's stark. Okay? So I told you this already. So for the last 5 large ruptures on this fault, it's been about 200 years recurrence interval. We're now at about 325 years. Why? Has the stress buildup changed? Has it been partitioned on some other fault? Possibly. So here, just to run you through some of our faults here in Southern California, we have about 45 millimeters per year coming in on the Imperial Fault. And it's partitioned on the San Andreas, San Jacinto, and Elsinore as such, 22, 12, about 5. And then we get to the Rose Canyon and we have about 1.5. And some of the faults offshore, we probably also have 1 to 2 millimeters of distributed deformation. Okay? So the large potential faults are the San Andreas and San Jacinto because of this deformation rate. Okay? So we've been out here, the green lines are survey lines where we've been out here for months in the Salton Sea. I've been in the sea there. I'm surprised I haven't grown another head, okay? But we've spent a long time out there, and the natives think we're kind of moving in, okay? All right? And so basically, we're really interested in trying to understand how deformation on this Imperial Fault is partitioned onto the southern San Andreas here and the San Jacinto Fault system here. All these red dots are earthquakes. Okay, we published this paper, Danny Brothers, who's doing a postdoc now in Woods Hole. We published the results of this in 2009, some of the structural interpretations. So here, as you can see, I'm wet up to my waist. I'm the guy that has to push the boat off the dock because they say I'm the biggest. They mean fattest. I don't look happy. So how does a chirp work? We are sponsored by In-N-Out. Scientists have to eat too, okay? And so here, this system emits a pulse. It goes down to the seafloor and it's reflected back and it comes to these receivers. So here it sounds just like that. It sounds like a 300-pound cricket. These transducers emit this very complicated signal. It reflects off the density and velocity contrast in the sediment layers. It comes back. We do some fancy math and collapse the signal to a spike. We get sub-meter resolution of the Earth. Okay? So we're able to see patterns that nobody's seen before. All right? Are we smarter? No. Do we have better tools? Yes. So here, the scale here is 100 meters. This is 7.5 meters. You can actually see this fault, and you can see the layers are offset. Here's the post-1905, the one everybody's familiar with, where the Army Corps widened the canal from the Colorado River and accidentally flooded the Salton Sea. Okay, and it filled up till 1907, till the railroad was able to close the breach. This is Lake here, 1, Lake 2, Lake 3. So this area of the Salton Sea is not man-made, okay? It's a natural system. It's been waxing and waning for millions of years, okay? So the Salton Sea is a natural lake system, and it dries out and it's flooded. And we're able to use this record to understand age dating in the flooding history. And so this is how it goes. So what we do is we look at faulting. We have an earthquake. We fault and we offset these layers from these layers. So we're looking now in cross-section like a road cut that you drive by. There's my earthquake. Then the sediment fills it in. So I'm looking for these divergent layers. Then nothing happens. Okay? There's my next earthquake. I offset these layers. So this is what I'm looking for, is I'm looking for these divergent packages in the sediment layers that tell me when things moved, okay? I also correlate this to onshore with trenched across the San Andreas Fault, which is right here. This is moving towards you, this is moving away, and we can actually go in and date very accurately the lake levels and the lake history. So we want to build a history because we want to know how often the fault moved in the past. And it's very detailed, and you can see the fine-grained lake stratigraphy, and then there's coarse-grained sand packages interspersed. Okay. We can also take the record we collect from the chirp that has high black smudges and transparent, and we can correlate this to cone penetrometer tests. The way the cone penetrates into the sediment tells the engineers whether the substrate is sandy, silty, or clay-rich. We can use this to correlate with our layers that we've correlated to onshore. So this here is a sand layer, and we gain confidence in that by correlating it to the onshore trenches and correlating it to the cone penetrometer tests. This is a picture of Danny deploying the chirp, and as I say, when you're in the middle of the Salton Sea, it's beautiful, okay? If there's no dead tilapia floating by. I can't eat tilapia, ever. Okay, so what happens? So here's the Colorado River. It discharges whatever little drips it has left nowadays in the Gulf of California. But it used to discharge a lot of sediment and water here, and then it would divert and flow into the Salton Basin. Okay? All right, so naturally this river would flow to the south, build up levees, then migrate back to the north. Okay? And it would do this through time. Okay, so let's kind of build stratigraphy here. Okay, so there's going to be a test at the end of this section. Okay, this is an experiment. We're in it together. Let's see how we do. Okay, all right. So here, it takes me 20 years of the Colorado River flowing into the Salton Sea to fill it to 13 meters above sea level, which is the sill that separates this basin from the Gulf of California. Present Salton sea level today is at minus 70 meters. So we add almost 85 meters of water. Okay. Right? So, and water's pretty heavy. And now the Colorado River is far away from the lake. You can actually go out into the Salton Basin and see the bathtub rings of where it was filled up to. Okay? And here, the sediment that's deposited in this deep, if I collected a core right here, is fine-grained clay. Fine-grained clay in our system is transparent. It doesn't make reflectors, okay? All right, so then I lower the sea a little, not too much. The rivers are still far away. The coarse-grained sediment that's fluvial is far from where my core is, so I still get fine-grained sediment. All right, so here again, the lake is full most of the time. This is Lake 5. We're going to just walk through now. Here, we lowered the lake for about 150 years, and we deposited coarse sand and fluvial sediment that on the seismic profiler gives a high amplitude return. Dark, high amplitude returns in seismic data is usually associated with sand. Transparent acoustic character is clay. Okay? So here, we fill it back up. We have deep water deposits. They're fine-grained. Here, we lower it for 180 years. We put in these coarse-grained channels full of sand. Okay, so here now I'm up to Lake 3. So I've gone through 6 lake secessions, building a stratigraphic core like the one I showed you. Sand, high amplitude, black reflectors, clay, transparent. Okay. All right, here's the test. Sand or clay? Sand. All right, you got it. All right, we're good. So here now you can see, look at this. This is the Salton Sea. We dried it out. Lake 1, dried it out. Lake 2, dried it out. Lake 3, really dried it out, okay? This was the Dust Bowl here. About 200 years of no lake. Lots of fluvial sediment. Then I have the next lake separated. So you can just go through this and you can actually pick the lakes, okay? And it's really a robust way to correlate the lakes around the sea, and we've done this. So what we've done is we've taken all these lake flooding desiccations, so it floods in about 20 years and it desiccates in about 60, okay? So all of these lake cycles, we believe we can correlate around the Salton Sea. Now, in the 2009 Nature paper, Danny discovered faults here in the middle of the sea that were never known about. These faults we labeled, he was very creative, and he called them H7, H8, and H9. As you can imagine, there's H1 through 6 too. Okay. So anyhow, these faults play an integral role in the story I'm going to tell you. So here, oh, one other thing is the San Andreas comes offshore, this bubbler, so we're right here. Water was bubbling up like a fire hydrant. We're in 10 meters of water, 30 feet. And the water is bubbling up, and it bubbled up for 4 months, okay? The guy we were with on the boat from the USGS just had this need to drive over this. I kept reminding him of the Japanese vessels that sank over active volcanoes. I figured I could swim to shore, so I got the life jacket and stood there while we went across this thing. And we got to the other side, and he said, "I told you we wouldn't sink." Amazing, okay? The volume of water that's coming up on this paleo trace of the San Andreas that comes offshore from the Bombay beach, it's amazing, okay? It has actually relief on the sea surface, okay? All right, so here comes the goods. So we sent Danny to Woods Hole in the wintertime. And if you've ever been there, you have two options. This is one, or going to the liquor store is the other. So he chose this, okay? So he traced all of these reflectors across fault H7, H8, H9, all of the faults. And he meticulously correlated them around all of this data grid that we had and built confidence on the offsets. Now here's what's really exciting. So we can take this data. So here's 2008, there's the fault, okay? All right. What we can do is in our computer, we can actually go back to the year 1360, and we can remove all of the sediment and deformation, and here, this surface F, which is offset here, flattens out, and there's no sign of the fault, okay? So this is how we try to reconstruct when the fault happened and the magnitude of throw. Now look what happened 40 years later. High amplitude sediment. Is the lake empty or is the lake full? Empty, right? We have sand, we have fluvial sediment, we have dark reflectors. The lake is empty and it's flooding. And right when we start flooding, which is shown here in gray, a little after that, whap, we have this event and we grow on this fault. So we have flooding. The flooding happens for a finite amount of time. We load the plate. This fault actually ruptures, okay, in the sea. All right? And we've done this for a number of the faults. And what we notice is when we look at our chronology and we look at our history of faults in the sea and on the southern San Andreas, we see 7 major events on these 3 normal faults, H7, H8, and H9. 5 of which occurred during flooding of Lake Cahuilla using the approach of seeing the high amplitude reflectors that correlate with sand, and we start flooding it, and we flood it for a finite amount of time, and then we see fault rupture and growth, okay? And 3, maybe 4 of these are coincident with events on the southern San Andreas. Why? Okay, so here, science, when you have observation, which we believe are pretty robust, you want to have some theory that links observation so you have some probable cause and effect. So what do we think happened? So this is work by Karen Luttrell. This is Coulomb failure stress, remember force. This here in this first panel A shows the Coulomb failure stress for a fault we identified in the basin. B shows for the San Andreas fault. And C shows for the static Coulomb failure stress plus the pore pressure. So what I'd like you to notice in the first models for just the southern San Andreas, a strike slip fault along here, actually loading the lake diminished the chances, it reduced the stress, and actually would make the region more stable. Okay? Before these new faults were identified, this was what was published in the literature. Okay? All right? Now you look at the new faults that we identified. So that's shown here in the blue. The blue is shown for the southern San Andreas. And here, this black line shows the accepted approximate triggering threshold, theoretically, about 0.1 megapascals, okay, this stress. What you'll notice is the Coulomb failure stress shown here, plus the pore pressure, the lubrication on the fault shown here, greatly exceeds the triggering threshold. So these new faults we identified, we believe are susceptible to loading of the lake. Well, why? So here, if you look at this diagram, this shows the Hawaiian Islands on the plate. And when you put the Hawaiian Islands on the plate, it's much like putting a couple of cinder blocks on a big sheet of plywood that's 1/4 inch, that's on horses. And it sags underneath. There's a deflection and bending shown here. Well, this bending, here's the water load with an unflexed lithosphere. When we actually bend the lithosphere like this, we put this part where H7, H8, and H9 are in extension, and these faults rupture. Okay? And the force is well beyond what's accepted as potential triggering stress. Okay? So it's the identification of these new faults that allowed us to understand maybe what the water loading was working on, because it wouldn't trigger the southern San Andreas. So now, how do these faults then load the southern San Andreas? So here, this is work by Debbie Kilb. Here in green is shown the new fault that we identified. It's shown here at 4 kilometers depth, and the red box is showing the face of the fault at depth. Okay? So here, this fault, when it ruptures, creates focusing of stress, one over here in the western Salton Sea, and one right here at Bombay Beach at the southern San Andreas Fault. And the magnitude of this is well beyond what we believe is a potential trigger. So now we have the link. The water bends the plate. The bending of the plate triggers these normal faults. H stands for hinge faults that we identified in the Salton Sea using our new approaches. These faults then load the southern San Andreas and potentially can cause rupture to go from south to north. Okay? So here, back to your stress and strain. So what we believe the water loading does is as the stress is building up on the southern San Andreas, we have lake loading, okay? And this lake loading actually triggers the earthquake before it builds up all the stress. So this added stress due to loading causes the earthquake to happen here. Okay? Really important to kind of understand propagation direction, because if it's from north to south, okay, the populated regions are much less. I come back, where earthquakes occur is really important for the loss of life. Okay? When they happen this way from south to north, heavily populated areas now experiencing more shaking for longer duration. Okay? So what I'd like to leave you tonight is this hypothesis that lake change triggers deep lake faults, which in turn we believe could trigger the southern San Andreas. Okay? It appears that it's done this, at least temporally, 3, maybe 4 times in the past. Okay? We've been diverting water from the Colorado River for about 100 years. So we've precluded the natural flooding of the Salton Sea. So it doesn't have this extra 85 meters of water that causes bending of the plate. Okay, so diverting the water has maybe made the time between earthquakes, the recurrence interval, to get longer, which could also build up the stress more, as I showed you in that plot. So here, this is in the Carrizo Plains, San Andreas. I'd like you to think about that earthquakes and lake loading, we know this from other areas and reservoirs. We know in 1906, when there was the flooding of Lake Cahuilla by the Army Corps, that there was an earthquake in this region, okay? But we only flooded it a few meters. Imagine putting 85 meters of water over an area that's 400 square kilometers. It's a lot of weight on the plate. And it happens very quickly. In that model I showed you, it's within the first 6-7 years that the load brings it up to a threshold that's acceptable as a trigger, theoretically. Okay? So here, very interesting feedbacks with earthquakes. Would propose that this might be the reason that there's been such a long delay since the last earthquake, but we need more dating and more study to understand this system completely. Just to leave you with this one thought, we're nowhere near, we're not even in the upper few hundred, okay? So the large earthquakes, remember, are on these subduction boundaries. So be happy that the ridge didn't want to subduct, and we're now a strike slip. Thank you. Let me repeat the question. The question is, we have a lot of water everywhere. The example is Hoover Dam. And did loading of Hoover Dam actually cause any earthquakes? In the Hoover Dam scenario, that you're not close to a major fault or triggering, but we do know in other dam regions, especially in China, that loading of reservoirs has triggered earthquakes. So two things that water does. One, that friction that between the blocks is lubricated, so you get a pore pressure, okay, that actually lowers the stress needed to cause an earthquake. And also, it works better for normal faults, not strike-slip faults. So the previous work by Karen and her advisor was a little ambiguous of whether loading Lake Cahuilla would actually increase the potential of an earthquake on the southern San Andreas, because for a strike-slip fault, that bending stress doesn't push it closer to failure. So it's not just the water loading, it's the style of faulting, okay? And the magnitude of water too, and how fast it loads in. So, but there are examples of reservoir loading that have triggered earthquakes. So the question is Palm Springs property value? No, is Palm Springs, regardless of whether the earthquake propagated from north to south or south to north, was highly susceptible to ground shaking. And a lot of the infrastructure where the groundwater and having sand and fluvial sediments, the example I showed you from the Sierra El Mayor fault system is in a very dry system too, but they irrigate it. So one of the things that we're starting to learn is watering your lawns. What does Palm Springs have? A lot of golf courses, okay, a lot of green. It's amazing for a desert to have green along the roadway. It's like an emerald jewel out there. So I think liquefaction could play a role. They're gonna have strong ground shaking there. So I would say that that's another effect. But the reason I brought up liquefaction is I wanted you to gain a realization that the epicenter could be here, and loss of life and damage could be far removed, but because of substrate, that these areas are at risk, okay? I'm gonna give you, this is, I take full responsibility for this statement. We have natural hazards here in California. We always think about tsunamis, fire, and earthquakes. So offshore of us is this morphology called the borderlands. And the borderlands has islands and great deeps and shoals. And if you're a surfer, there's certain places offshore that during big northwest swell from the Alaskan low, you get out there because the waves really break and curl, okay? So when a tsunami would approach anywhere from Santa Barbara south, the offshore relief being shallow then deep and shallow then deep, imagine the wave comes in, it starts shoaling, and it reaches a certain L/20 water depth where a wave reaches up and spills, all right? But then it gets deep again. So what happens is repeatedly the wave tries to build up and then it gets deep again. So offshore Southern California, we have morphology that acts as a natural baffle to tsunamis. North of Santa Barbara, Okay, Humboldt County, Trinidad, they've had tsunamis and loss of life. Okay, because they don't have this offshore morphology called the borderlands. Earthquakes here in San Diego, I'd say we're very safe. If your house is on rock or hard ground, if you're on loose soil or bay fill, you might be a little more susceptible to liquefaction like I talked about. But I would tell you the biggest fear I have living here is burning down. Okay? Well, I think that we stayed in the realm of probability. We were telling you that we think we see causal connections in the past. Nowhere did I say when an earthquake was going to happen. So Howard's question, just to repeat it, is I emphasized repeatedly in my lecture that we cannot predict earthquakes, okay? And we cannot. So he asked me, what am I doing with all of this? I have no idea. No. What we're trying to do is we're trying to build a record through time at how often these things occur. And we're also trying to understand other loading processes besides just the plate tectonic process that might allow an earthquake to trigger below the stress you'd predict just by tectonic processes alone, right? I think what we've seen in earthquake research is that these probability maps I showed you have gotten much better. We understand better the distribution of strain on the faults, how it's partitioned. We also understand other components such as liquefaction and how that influences infrastructure. I think that the problem with friction and rock properties, because we don't know all of the different rock properties, and we don't know exactly how the stress is distributed, and we don't know all the faults, like the Northridge Fault. We didn't know that fault was even there. So I think that we're getting better, but I still think predicting earthquakes, we're going to still be in a probability pattern of trying to illuminate which areas have the greatest probability in certain time intervals. The question is, about 45 millimeters per year comes up on the Imperial Fault, and then it splits with about 22 going on the San Andreas, about 17, 18 on the San Jacinto, about 5 on the Elsinore. And the question was, is this through time robust, or does it temporally change? And these are some of the questions we're trying to get at. Really hard in the past, because finding it, we call them piercing points. So you want to find areas where you can confidently connect up a stream valley or some feature that crossed the fault so that you can integrate how much movement's been across that fault. And these measurements are very difficult. But I would tell you that these rates evolve through time and change. But what kind of magnitude they change, we just don't have really good constraints. We have very good constraints from GPS arrays of how the plate is accommodating this deformation today. And it gets more and more uncertainty as you go into the past. Very good question. I think that filling, and you're talking about the Air Quality Act with LA about putting more water back into Owens and Mono Lake. I think that the magnitude of water that you'd have to put in, LA is never gonna let go of. So I think that they're gonna bring it to some stable scenario, but they'll never flood it like it was, you know where Fossil Falls are? So imagine what it must have looked like back then. Isn't that, it's just when you drive up 395 and you just look at the morphology and how large that lake and all those multicolored beds right when you go by Big Pine, you know that road you can take up into the bristlecone? All of those are lake bed, the Wakabi wake bed deposits. And so it was filled very high up in the valley. And so that would be, you have the Sierra Frontal Fault. The Sierras are pulling away from North America at about 10 millimeters per year, and that gave rise to the Lone Pine earthquake. Okay, so there's potential for large earthquakes in Owens Valley, Panamint Valley, and Death Valley. So I don't think they're going to fill it to a point where it'd be a concern, but I'd hate to see filling it to back when it was really moist about 13,000 years ago. So does pumping water out of the ground have similar impacts? And it could, but in this instance, that would probably lower the susceptibility to earthquakes. So the loading is what's really causing this bending moment, which is causing these normal faults to rupture and then load the southern San Andreas. Okay. So the question is because of the diversion of the Colorado River water and not loading the sea, are we now more susceptible to a fault that's going to propagate from north to south? We're just starting to learn about the importance of propagation direction, and our group was able to understand some linkages that might explain a south to north. But I think a north to south, there's a lot of complexity that would govern which way it would go. And so I don't think that increases the chances, but I think that propagating from one direction to the other is still what causes these things to happen, and propagation direction requires further study. So I don't think it increases nor decreases. I think our just knowledge base isn't in depth enough to make, guesstimates on that. So here, the lake deposits. So what we've been able to notice is that we've identified about 12 lakes in this valley, and they go back on the order of thousands of years. But before that, millions of years ago, this was an inland sea that the Gulf of California connected all the way up into the Salton Trough, and we know that from the deposits and evidence halites and deposits that are indicative of a marine environment. And the Colorado River, before diversion and damming Lake Mead and all the lake systems on there, diversion of water, when you had big snow years, the river would come down and it would try to go through its meanders, but it'd be flooding. And so what would happen is it would have what we call an avulsion. And the water breaks out of one of these meander belts, and it just depends, it's like flipping a coin, whether it breaks out to the south or to the north. Okay, and this is just a natural part of a river system. And so it's just the inherent variability in river dynamics that causes whether it flows to the north or south. Thank you very much. It's always a pleasure coming in.